Last reading, we talked about what makes a good abstract data type. And the final property of a good abstract data type that we want to spend a lot of time talking about is that it should preserve its own invariance. So what does that mean? Well, an invariant is a property of a program that is always true for every possible runtime state that the program can get into. Immutability is one crucial invariant that we've already seen. Once you create an immutable object, it always represents the same value for the entire lifetime of that object. No matter what states the program goes through, that object should represent the same thing. So saying that an ADT preserves its own invariance means that the ADT is responsible for ensuring that its invariants hold. It doesn't depend on good behavior from its clients. Now, when an ADT preserves its own invariance, reasoning about the code is much easier. If you can count on the fact, for example, that a string never changes, then when you're debugging code that uses strings, you can rule out the possibility that the string might have changed under your feet. Or when you're trying to establish an invariant for another ADT that uses strings, you can count on the fact that the string won't change. Contrast that with a string type that guarantees it will be immutable only if its clients promise not to touch it. Then you'd have to check all the places in the code where the string might be used to make sure the clients are upholding that promise. Let's start by talking about immutability. We'll see more interesting invariants later in this reading, but immutability is a good one to start with because we're already familiar with it. Here's a specific example. This is an immutable abstract data type. It's supposed to represent a tweet from Twitter. And a tweet has three properties. It has an author, that's a string. It has the text of the tweet, that's a string. And it has the time that the tweet was sent, which we'll represent with a date. And this has a single creator operation, which takes that author text and timestamp and packages it up into a tweet object. And then the observer operations are basically these fields, which are public. So you can get the author, you can get the text, and you can get the timestamp just by using .author, .text, and .timestamp. Now we said we wanted it to be immutable, so how do we guarantee that these tweet objects are immutable? Once a tweet is created, its author, message, and date never change. Well, there's a bunch of threats to immutability here. This is not a very well-designed data type if it wants to be immutable. The first threat to immutability comes from the fact that clients can directly access its fields. In fact, they have to directly access its fields in order to find out what they are. So nothing is really stopping us from writing code like this, constructing a tweet object and then directly reassigning the author of that tweet object to a different author. This means that the tweet is not really immutable. This is also a trivial example, a simple example of an idea called representation exposure, which is a risk to abstract data types, meaning that code outside the class is allowed to modify the representation directly. Rep exposure like this threatens not only the invariance of the abstract data type, but also representation independence, which we talked about in the previous reading. In other words, we can't change the implementation. We can't allow the implementer to use different definitions for these fields without affecting all the clients that are directly accessing those fields. Fortunately, Java gives us language mechanisms to deal with this kind of rep exposure. These private keywords indicate which fields and methods are accessible only within the class, and the public ones indicate which ones are accessible outside of the class. So now we can create explicit observer methods that allow you to get the author and the text and the timestamp. And that's what a client will be able to use, but they won't be able to use these private fields. This final keyword, which we've also talked about, also helps by guaranteeing that the fields of this type of tweet cannot be reassigned after the object is constructed. But that's not the end of the story, because the rep is still exposed. So think about this perfectly reasonable client code that uses tweet. So it takes in a tweet t points to this tweet object. It gets the timestamp of that tweet, which remember we'd said would be a date. So it gets that timestamp and puts that in a local variable d. And so now note, d and timestamp are both pointing to the same date object. And then what we want to do is add 1 to the hours of that timestamp and create a new tweet that is an hour later but has the same text. So it's like retweeting it. So we add an hour to this date and then we're constructing a new tweet object, which isn't being shown here. But the problem is that that mutation, that set hours, changes this same date object that the original tweet T was depending on. Get timestamp returns a reference to the same date object referenced by tweet T.timestamp. T.timestamp and D, in other words, this arrow and that arrow, are aliases to the same mutable object. So when that date object is mutated by D.setHours, that affects the date in the timestamp T, in the tweet T as well, as it shows in the snapshot diagram. So we've broken the immutability invariant of this tweet. We've actually changed the timestamp of the original tweet. Fundamental problem is the tweet leaked out a reference to a mutable object that its immutability depended on. We exposed the rep in such a way that tweet can no longer guarantee that its objects are immutable. And perfectly reasonable client code that thought it would be harmless created this subtle bug. Now, we talked about this in some sense before when we talked about returning mutable objects from a method. We can patch this code by using defensive copying. In other words, making a copy of a mutable object to avoid leaking out references to the rep. So here's the code that does it. This makes a new date object using the same timestamp that happens to be in that date object. Many mutable types often have a copy constructor. In other words, it takes one instance of the type and produces an identical instance with a different reference of the type. In this case, date's copy constructor is a little bit weird because you have to first get the timestamp value measured in milliseconds since January 1st, 1970. String builder's copy constructor takes a string, so you have to turn the other string builder into a string before you can create a second string builder from it. There is in Java another way to copy a mutable object called clone, which is supported by some types but not by all. There's some unfortunate problems with the way clone works in Java. If you want to learn more, Google for it or look at item 11 in Josh Bloch's wonderful book, Effective Java. So we've done some defensive copying in the return value of get timestamp, but we're not done yet. There's still a rep exposure here. So consider this perfectly reasonable client code. We've got trying to write a method that is going to generate a list of 24 inspiring tweets, one for each hour of the day today. So it makes an array list. It gets a date, and by default this is going to give you today's date, and then runs through the hours from 0 to 24, 0 to 23 actually. And for each one, it changes this date so that its hour is I, and then it creates a new tweet with that date, and for now just the same message. We probably want this to be different inspirational messages, but for now we're just going to do 24 of the same message. So we end up with an array list of 24 tweet objects. Now what's wrong here? Well, the problem is that each of those tweet objects is now pointing to the same date object, right? We passed in this date object here and we were just mutating it as we went along. All 24 tweet objects end up at the same time, which happens to be, hour 23, the one we finished with. So again, the immutability of tweet has been violated, right? We constructed these earlier tweets intending them to be at the earlier times, 0, 1, and 2, and so forth, but they all ended up being changed after the fact. And the problem was that this date object that we were passing in just got put into the representation of the tweet, even though there were still aliases to it being held by the client code. So we can fix this problem too by judicious defensive copying, this time in the constructor. Before we store that timestamp, we make a copy of it. In general, to avoid these kinds of rep exposure, you should carefully inspect the argument types and return types of all your ADT operations. If any of them are mutable, then make sure your implementation doesn't store or return direct references to its representation, because doing that will create these kinds of rep exposure. Now you may complain that this seems wasteful. Why are we making all these copies of dates? Why can't we just solve this problem with a carefully written specification? It says something like, caller must never mutate this date object again. This approach is sometimes taken when there isn't any reasonable alternative. For example, when the mutable object is too large to do copying efficiently. But the cost of this and your ability to reason about the program and your ability to avoid bugs is enormous. The absence of compelling arguments to the contrary, it's almost always worth it for an abstract data type to guarantee its own invariance, and preventing rep exposure is essential to that. Now, an even better solution to this problem is to just use immutable types. If we had used an immutable date object like Java times ownDateTime instead of this Java util date, then we would have ended this section a long time ago. No further rep exposure would have been possible, and that's exactly what we got with strings. There are immutable wrappers around mutable data types. The Java collections classes offer an interesting compromise to that. We've talked about collections unmodifiable list, which takes a list and wraps it with an object that looks like a list, but whose mutators throw exceptions. So you can construct a list using mutators and then seal it up in an unmodifiable wrapper, and you get an immutable list. And then that's safe to return from an observer method, for example. Downside is you get immutability at runtime, but not necessarily at compile time. So if you call a mutator like sort on this unmodifiable list, Java won't warn you. You'll just get an exception at runtime, but that's still better than nothing. So unmodifiable list maps and sets can be a very good way to reduce the risk of bugs.